Electrochemistry Video 1. First we need to revise some background knowledge. What is the meaning of the term atom and the term ion? An atom is neutral, whereas an ion is charged. This is because an atom has equal numbers of electrons as protons, whereas an ion has unequal numbers, because it has either gained or lost electrons. A positive ion, also called a cation, has lost electrons. A negative ion, called an anion, has gained electrons. An example of the formation of a positive ion, a cation. Beryllium is a neutral atom. It has just as many protons, which is 4 in its nucleus, as what it has electrons spinning around it, and so it is neutral. But it has 2 valence electrons, which if lost would reveal an underlying core which has an electron configuration the same as a noble gas, which is stable. And so these 2 electrons will easily be lost, and that will cause the beryllium atom to change into a charged beryllium ion. And now we still have 4 protons in the nucleus. Every single instance of beryllium has 4 protons in the nucleus, otherwise it would not be beryllium. But now we only have 2 electrons spinning around that nucleus, and so we have 2 more protons than electrons. The charge of the beryllium ion is 2+. Now let's look at the formation of a negative ion, an anion. Non-metals can form anions. Fluorine is an example of a non-metal. It's a halogen. It's found in group 7, which is right next to the noble gases. Sometimes in some systems group 7 is instead called group 17. Now in the first picture it's shown in the atom form, meaning that it's neutral. It has just as many protons as it has electrons. It has 9 protons and it has 9 electrons spinning around it. 7 of these 9 are called valence electrons, outermost electrons. 2 of them are called core electrons. Now a substance is most stable if it has the electron configuration of a noble gas. Now the nearest noble gas for fluorine is neon, but neon differs from fluorine in that it has 10, not 9 electrons. It has 8 valence electrons, not like fluorine has 7 valence electrons. So for fluorine to become stable like a noble gas, it needs to gain another electron, in which case then it would have a neon electron configuration, and that is what often happens to fluorine, and in so doing it changes the fluorine atom to the fluoride ion. We no longer call it fluorine, we call it fluoride, and the fluoride ion has 8 valence electrons, or we could say 10 electrons altogether, since it still has the 2 core, of course, and so it has a neon electron configuration. Notice it isn't neon because its nucleus is still that of fluorine. It still has 9 protons in the nucleus, whereas neon has 10 protons in the nucleus, but its electron configuration is like neon's. It has 10 electrons in its electron shells, and that means that it has 1 electron more than it has protons, and so it has a charge of -1, so we write the fluoride ion as F-1. It's very important to realize that the properties of atoms and the properties of ions of a certain element are completely different. For example, sodium in the atom form is a shiny silver metal. If you put it onto water, it reacts explosively with water, releasing hydrogen in an exothermic reaction. But sodium, the ion Na+, if it's reacted with chloride, for example, then it's sodium chloride. It's table salt, which is a white brittle salt. It dissolves in water. There's no explosion. It's not flexible. It's not silver. We can see sodium, the atom, and sodium, the ion, are completely different in properties, and so it's very important to distinguish between them. So if we have sodium chloride, table salt, NaCl, although we write the formula as NaCl Cl, suggesting that we have sodium atoms in there. It's not so. It is actually sodium ions that we have in there. So a better way really of writing sodium chloride, I suppose, would be Na plus Cl minus, but we tend not to do that. And so you just have to realize that sodium chloride does not contain sodium atoms. It contains sodium ions, and it doesn't contain chlorine atoms. It contains chloride ions. Another thing about sodium chloride is that it's a giant molecule. So although we write NaCl as if there's one sodium bonded to one chlorine atom, that's not what it's like. In fact, the ratio of sodium to chloride ions is just 1 to 1, but the actual numbers of sodium ions in a particular sodium chloride molecule is, well, a huge number, so we don't write it. But what we know is that as many sodium ions as there are, that many chloride ions there would be in a sodium chloride giant molecule. The ratio of sodium ions to chloride ions is 1 to 1. And here we can see just a small section of a giant molecule of sodium chloride. And this is only a 2D representation. You must actually try and think of this three-dimensionally, extending for many, many thousands, maybe even millions of sodium ions and chloride ions in each of the 3 dimensions. The next thing we need to revise is what happens during dissolving. In the case of an ionic molecule, which is a giant molecule, dissolving involves the ionic crystal being dismantled, being pulled apart into its separate ions, which are hydrated. In other words, surrounded by water and therefore in the aqueous solution. This is a pictorial representation of the process. We start off here with some sodium chloride solid. A section of the crystal is drawn here where we have regular packing of sodium ions and chloride ions, and then water is added to this. Now water molecules are polar. Because of an electronegativity difference between hydrogen and oxygen, the electrons in the bonds are not equally shared. The bonds are polar. Oxygen has a greater electronegativity than hydrogen and so pulls the electrons stronger to itself. Because the water molecule is angular, it is not symmetrical, therefore the molecule as a whole has a polar negative end on the oxygen side and a polar positive end on the hydrogen side. Now since that is slight, as in it's not an ionic substance but just a polar molecule, we represent these differences in charge with the Greek small letter d, delta, small letter delta, and that means slight. So there's a slight positive charge on the hydrogen end and a slight negative charge on the oxygen end. It's a polar molecule, and because it's a polar molecule it can exert electrostatic forces, and that it does on the ions of the sodium chloride. And so it orientates itself, like here we can see the hydrogen end, which is positively charged relative to the oxygen, is orientating itself near to the chloride ion over here, and that causes the chloride ion to be pulled away from the crystal lattice, and then it gets dissolved by being surrounded by a number of these water molecules, all with their hydrogen ends pointing towards the chloride ion. And meanwhile the sodium ions, they get surrounded by water molecules such that the oxygen's end is nearest to the sodium ion.